Okay, perfect. Good afternoon, everyone. My name is Faria. First, let me start by thanking the organizers for the opportunity to speak at the EPRV today, and also for the opportunity to attend the conference remotely. That does mean that it's 1:30 in the morning here in Porto, so I hope I can still make a coherent train of thought, but let's go on. So I meant to talk to you today about a Bayesian workflow for planet detection in radio velocities. That was a bit of an optimistic title, and so I'll only focus on a small part of this workflow because this is very much a work in progress. And so I'll talk about building or trying to think of a model that can be a bit more interpretable and a bit more robust to deal with planet detection in radio velocity. So first, let's just go very broadly at it. And we, as Bayesian, as data analysts, what we want to do is to connect the true physical system, the planetary system that we are interested in, to the data that we observe of the universe, of this system itself. And so we want to build this connection and understand, by looking at the data, understand the system we are looking at. And we do this by building a model. And building a model, in particular for precise radio velocities, implies defining parameters that we're interested in, the orbital parameters of the planets, for example. And then if we're working on the Bayesian framework, we need to assign priors to each of these parameters. We need to think of assigning as well the likelihood, which is often something that we go over fairly too quickly. And then we need to perform inference on this model. And later on, we might have to take some decision on what we learned, on the values of the parameters that we learned, and to connect them to the reality. Then we can also make some assumptions and ignore complicated things like our activity, which is what I will do for the remainder of the talk. So I'll only focus on the Keplerian part of this radio velocity model. So we now can do this fairly in a standard way, as Nathan was just showing you. We can even include the evidence calculation for a given number of planets, and then try to do model comparison for a given data set. And we do this for 0 planets, 1 planet, up to 6 planets. We keep seeing the evidence increase, so the model keeps getting better. And then at some point we need to stop. That's okay if we do it step by step like this. And just to point out that a few EPRVs ago, we were not so, let's say, we were not doing these evidence calculations as robustly as we are now. But this has evolved, and we can now claim to calculate the evidence with some accuracy. But again, doing this iteratively and step by step is maybe not optimal. And so what we can actually do is add, since we don't know it, the number of planets, we can add it as a parameter for in this model. We have to now assign it a prior, and we can use a uniform prior up to some value. This works fairly well. In this case, we're using a uniform prior up to 6, and we get automatically a more efficient search for this best model. And we look at the posterior for the number of planets, and it gives the best model. This also poses new challenges, because now we don't necessarily know what's the maximum value we should consider, what's the prior we should consider. And so we need to be in this stage where we are doing model comparison and looking at posterior, comparing models one to the other, finding criteria to do that. So that's the complication. And so my thought here is a simple thought process. Let's say that we want to replace this model with a different one. Instead of modeling a given number of planets in this data set, we want to model both the Keplerians that we can detect in this data set and the ones that we cannot. And so these two components, these two different components. And we are actually, in the end, just interested in the ones that we can detect, and the others are just nuisance in some sense. But let's divide the model like this and see what comes out. And what distinguishes these detected from these not detected Keplerian is to some sense, to some extent, just the amplitude of the signal. So if the semi-amplitude, if k is large enough compared to something which we don't have to specify yet, then the Keplerian is detected. If it's not large enough, but it might not be necessarily equal to zero, then this signal is not detected in this data set. And so at the same time that we make this new interpretation, we can also think of a prior for the semi-amplitude that might also be a bit different. So instead of, as is typically done, we consider what I'll call a spike and slab prior, where we push all the non-detected Keplerians to have k equals zero. We can allow for these narrow and broad components that will be separated at some transition value that now allow for a bit more wiggle room for the non-detection. The components that are not detected in this data. And so, broadly speaking, k is now assigned a different prior depending if that Keplerian is detected or not, and also depending on that transition value. But since we don't know a priori which is which, what we actually do is to set up a mixture prior for the semi-amplitude, where we say that with some probability it's not detected, with a probability m it is part of the detected Keplerian component. And so this m just takes values 1 or 0 depending if that Keplerian is detected. And now we have a number of new parameters m which are free to vary in the model. So there they are, and they connect directly to the prior for k. So these are sort of hyperparameters in some sense. Then we can also, so we have to assign them prior. They are now parameters, and we can start by simply assuming equal probabilities for detection and non-detection. So m, the different m's can be 0 or 1 with equal probability. And if we now analyze that previous data set with this new model, what we find is the posterior distribution for these parameters and for each of the 10 components. I'm considering up to 10 components. And now we have an interpretable value right off this model, which gives us the probability of the Keplerian k having been detected in this data set directly from this posterior distribution. You will notice that in this case, we recover the previous result that I showed you before in the distribution for the planets, in that the actual probability, the posterior probability for there being 10 planets is about 0.8, 0.77. And so in this case, the previous result is recovered. Why is that? Well, that's basically because I told you that we built this new model, but we did this assumption that the probability of detection and non-detection is same 50%. But actually, we can go one step further into this model and then define this new Bernoulli prior for the m values to depend on. So it will depend on the probability of m being equal to 1, which we'll represent by a value p. And then we build this hyper prior for p now that we define as a beta distribution of some parameters alpha and beta. Furthermore, if we note that the sum of all the m's will give us the number of planets detected, then this effectively transforms, or effectively follows that now the number of planets detected and p will follow a beta binomial distribution a priori with parameters and p max, alpha, and beta, right? And so as you see here, our previous assumption of equal probability of detection and non-detection just gives a uniform prior for NP, which is what I assumed before, and that's why we recovered the same results. But nothing is stopping us now from actually playing a little bit with the values of alpha and beta, and so changing our prior assumption about the number of planets that we can detect in a given data set, and so we can increase or decrease the probability of having a detection or not, right? But because of this new interpretation, what's the advantage of it is that we can now actually use our current knowledge of planetary systems, what we know about planetary systems, to inform this prior for NP. And so my point is that this NP now represents the number of planets of Keplerians that we detect. And on average, we detect 1 planet for every 3 stars. And so this actually sets constraints on the expected value, the average value for NP a priori. And therefore, it can also set constraints on the ratio between beta and alpha if we fix one of these parameters. In this case, I fix alpha equals to 1. And so by using this prior information from what we know about planet detection with radio velocities, I'm able to come up with a prior for NP that is motivated by the true prior information that we have. And if I use now this prior information, this actual prior for the P and for the different M values on the previous data set, what we get at the end is again an interpretable value right off that gives us the probability of a given Keplerian being detected, but that now is much more in line with our prior information about radio velocity detection. And so there is that advantage that we can now interpret without going into the complications of doing model comparison. We are somehow automatically getting an interpretable value, interpretable posterior probability of detecting a given Keplerian component. And so that's about it that I had to say, and just some take-home messages to summarize this idea. We thought of a way that we could reinterpret this more or less standard radio velocity model to have these 2 components, these 2 Keplerians that are either detected or not in a given data set. And then we assign the mixture prior to the semi-amplitude K with a transition value to separate these 2 components, which is different than 0 in this particular case. And then the mixture weight, that M value, gives you directly the probability that the K component is detected. And so it provides a clearer interpretation as a direct probability of detection. Okay, that was sort of the goal here, to try to reinterpret the model in order to get this interpretability. And then finally, every time we're doing Bayesian methodology, we're using Bayesian methods, we need to be a bit careful about the priors. We always need to consider the implication of our priors. And as I showed you, sometimes the prior that seem reasonable at first glance, for example, the priors for the number of planets, don't actually encode our prior information that we do have, right? And so with this model, we could see that there might be an easier way to encode that information from prior knowledge. Okay? And so I will finish here, and I'm happy to take questions either online or live now. Thank you very much.
Thank you, João. Are there any questions?
Hi, thanks, João. I'm just wondering if you have some information about the detectability, doesn't it mean that you have somehow an information on the threshold, on the detection threshold, which is encoded in the prior?
Yes, so this K, I can hear myself a bit, but okay. This KT, the transition value, I think it's what you are referring. This somehow you need to estimate this value. I've glossed over those details. Here I'm actually using, this is also a free parameter in the model, and I'm actually estimating it from the data with reasonably tight prior, because there is little information in the posterior, in the data about this parameter. I think that's what you meant. I'm not sure.
Yeah, okay, thanks.
Any other questions? Joe, I was actually also wondering about the K sub t, because it seems like your parameterization depends on it being a constant, but wouldn't you expect it to vary with period, for example?
That's an interesting question. I think in practice, not, because this would mean that that's an interesting question. I'm still thinking about it, whether it should or not. I don't think so, because it means that a long period signal could still be detected in the data with down to a given amplitude. And that could be the same as a shorter period signal. But I'm still thinking whether or not we need to input that dependency into this value. That's a very good question. Thank you.
Okay, I'll ask you again when it's not 1 a.m. your time, maybe. Let's thank Joe again.